Hi, everyone. Thank you so much for inviting me to be here today. This has been a fantastic day of wonderful talks, and I've already learned a lot. Today I'll be talking about how we have used refinement proofs to prove safety properties about cyber-physical systems that are complex. And then the second half of my talk, I'll talk about how we might also be able to use these same refinement techniques in order to prove properties about those same cyber-physical systems, but now with intelligent controllers. One asterisk on this talk, I recently graduated from CMU, and so a lot of the work that I'm presenting here was actually done in my PhD here at CMU, and also comes out of research groups here at CMU. So there's a little bit of Google stuff in there, but for the most part, this is also academic research. All right, so let's start off with an example. So here we have a multi-lane highway with lots and lots of cars. Each car is able to change lanes or enter or exit the system. And what we want to do is verify that if these cars are controlled by some computer controller, then that computer controller won't cause them to crash into each other. So for example, if I'm driving along and the car in front of me slams on its brakes, I might have an emergency braking system in my car that would keep me from colliding with the person ahead of me. So this system is complicated, of course, because it's a cyber-physical system and has these physical dynamics that we have to analyze. But it's also complicated because we have distributed dynamics. So we have hundreds of cars on the road all at the same time. You don't just want to make sure that your behaviors don't cause a crash for the person directly behind you. You also want to make sure that you don't do anything in your lane that causes a crash multiple lanes over, or maybe even a mile back on the road. There's some emergent behavior that sort of has a domino effect later on. So we want to verify these systems as a whole in their global setting. Another system that we've looked at is distributed aircraft control. So here we wanted to look at a collision avoidance maneuver for aircraft, where each of the aircraft are flying around independently, and they needed to resolve conflicts between each other in real time, essentially. So this is complicated. It still has all the distributed dynamics of the car control system, but we also have even more complicated physical dynamics. So we have to get the differential equations right around how these aircraft move around in space and make sure that really they do have enough space to avoid each other. And for aircraft especially, they can't just come to a stop on the shoulder like a car, right? We have to make sure that they don't stall. So we've looked at a whole bunch of these kinds of case studies. And there are sort of unifying aspects. So each one of these case studies pushed the boundaries of what we were able to verify in terms of cyber-physical systems in one way or another. And they had this unifying aspect that they all sort of found the right abstraction layer. So they found the right abstraction of the system that we were trying to verify by modeling it at a level that formal methods were then able to say we can take this apart and actually analyze it and come up with an answer for you, yes or no. There is a crash or there won't be a crash. So for example, going back to the highway case, what we did was we first started by verifying that two-car case and used that as a lemma to be able to prove that cars are safe on a single lane, and then used that as a lemma to prove that the entire highway system was safe. So by breaking the system into these, basically distilling it into the most essential components and the basic building blocks of a system, we were able to take these very complicated systems and actually make some conclusions about them as a whole. However, a lot of these systems, actually all of the systems that we looked at, don't explicitly model any kind of intelligent controllers. They just sort of abstract away the controllers and say, well, as long as the controller satisfies this set of values, so my controller doesn't go outside of this range in this set of circumstances, then I can prove safety. And I kind of leave it up to the programmer to decide how they're actually going to implement that. Just kind of hand-wavy. So why are we talking about AI? Why can't I just say that my job is done? You know, I verified this range of values that are safe. Well, AI is special, and AI is special because it allows us to react even in unpredictable situations. So for each of these, for autonomous cars or any kind of cyber-physical system, what we see in the environment is far beyond any set of expected behaviors that we could write down ahead of time. You can say, like, for the Tesla example from yesterday, Tesla should have written down that there are orange cones on the road and it should know to avoid those and identify them. Well, there are a lot of different shapes of orange cones. Or you should write down that, you know, lanes end this way or lanes go that way, or this is the behavior, and this is exactly how your autonomous car should react to each of those different situations. But we can't even enumerate all of these situations, let alone have time to write them down and figure out how to respond. So we crucially depend on artificial intelligence to be able to do the right thing or do a reasonable thing in any situation. Okay, well that's tough, because if I'm not exactly sure what my intelligent controller is going to do, or if I have to verify it against these unexpected situations, this is now a controller that's going to be extremely difficult to verify directly, because we have this, this intelligent controller that is extremely complicated. So now it's too tough to verify. Okay, so what can I do? Well, taking away the AI component again, looking back at some of the work that we've done, we've used a concept called refinement, which I'll talk about in this talk, which has allowed us to verify systems that were previously out of scope. So for systems that were too tough to verify, we would use refinement in order to verify them even with their complicated dynamics. The second part of my talk will focus on how we might be able to use that same technique and apply it to intelligent controllers. And then finally, I'll look at real-time monitoring, which may allow us to check that the models that we've come up with are actually valid models for the state in real time when the system is running. Okay, so Jeanette told you a little bit about logic, and if you can remember everything that she showed you on that slide, you'll remember that we really want to specify a model of our system, here depicted as an airplane, and some property that we want to show that that system always satisfies. So I just wrote safe to imply something. It could be safe separation of aircraft or any number of things. And then we put that box around it from temporal logic to say that all possible runs of that controller will keep you in a safe state. And we have to limit this, you know, we can't just say whatever state that these aircraft start in, we're going to be able to control them. We have to start them in some controllable initial state. So we can't have two aircraft about to collide and then say, good luck, computer, you know. That's a little bit too much of a challenge. So we start with these, some aircraft that are satisfying these initial conditions, and we look at all the possible trajectories that that controller might take. And we check that in every case, they end up in a safe state. And in fact, all the way along that trajectory, they satisfy that safety property. And possibly there's an unsafe state out there, maybe with another aircraft that would get too close. But we don't go there. So this is what we mean when we say that some aircraft can be verified safe. The next property that I want to talk to you about is sort of a new one, and this is the idea of refinement. So does one system of a refinement of another? And essentially what this is helping us reason about is, when I make a new system, is it at least as safe as the system that I had previously deployed? Okay, so here, it's a little bit counterintuitive, but that less than sign is talking about the behavior of the system, the reachable states of the green system versus the blue system. So here we have, again, that model of that blue aircraft and all the states that it can reach, versus the green aircraft, which can only reach a subset of those blue states. So in this case, the green aircraft is a refinement of the blue aircraft system because it has a subset of the reachable states of the blue system. When we combine these two concepts, refinement and safety proofs, that's where we get our real power. So here, I've got a safety proof. Suppose I have a safety proof of my blue system. But what I really want is a safety proof of this green system. But the green system might be really complicated, and I haven't been able to prove it so far with traditional methods. So instead, I will leverage the fact that I already have a safety proof for the blue system, and I'll just show that there's a refinement relation satisfied. And as a result, because I know that everything accessible by the blue system was safe, I also know that everything accessible by the green system also satisfies safety. By adding this refinement relation to our proof calculus and our theorem prover, we can now sort of like ratchet up the complexity of the systems that we're able to prove. So we can start with that blue system, which we were already able to prove, and then say, well, what I'm really interested in is that green system, and so now by relating the two, we can like ratchet up the complexity of the systems that we're able to verify. Okay, so now that we have this tool, this refinement tool, maybe we can analyze some of the basic paradigms that we have around modeling controllers for cyber-physical systems. And one of the standard divisions is around event-triggered systems and time-triggered systems. So on an airplane, often the way that you will receive information about your surrounding environment maybe is through like radar or communication. And what that looks like is something discrete, something that's periodic. So you send out a radar ping and you get occasional information about other aircraft in your area. But you don't have constant access to that information. You don't always know the full state of the world. And that means that you have some delayed reaction time. So as an aircraft might come up and be very near you, and it might be you have to wait for that next ping to be able to actually detect that aircraft. On the other hand, the event-triggered system assumes continuous sensing. So it thinks, okay, well, as soon as I get to this distance from that other aircraft, then I'll start to turn around and avoid it. But it doesn't have to worry about this sort of delayed response time. So which one is better? Well, they're just kind of different, right? So discrete sensing is a little bit more representative of what the real world looks like, whereas continuous sensing is a little bit unrealistic. But event-triggered systems have a lot of benefits. Specifically, they're easier to design controllers for because you don't have to think about this delayed response. And they're also significantly easier to verify. Whereas time-triggered systems are difficult to design and also even more challenging to verify. But when we look at these two systems in terms of refinement, with this refinement framework, we find out that they're actually not so different after all. And we can establish a formal refinement relationship between the two, once and for all, where now we can sort of have our cake and eat it too, where we start with an event-triggered blue system and we prove that, and then from there we refine it into a time-triggered system and leverage that event-triggered proof to actually be able to more easily prove this time-triggered system. And that time-triggered system now more closely represents the system that's actually going to be deployed in the real world. Okay, so I'm going to sort of conceptualize these as the event-triggered system has a larger set of reachable behavior, and we refine it into this smaller time-triggered system. But now what about AI? Can we use this same kind of reasoning to talk about artificial intelligence controllers? So here, because this refinement property works even inside of a subsystem, as opposed to the system as a whole, we can look just at what that time-triggered, the subsystem, I don't want you to necessarily understand this, but basically we can look just at what that time-triggered system has as a controller. And what it's giving us is a set of values that controller is allowed to choose from. And then when we have some complicated artificial intelligence, which I'm just putting as some function theta, we have just a couple formulas left that we have to verify to show that that artificial intelligence function actually satisfies whatever controller requirements were laid out by that time-triggered controller. There are a couple ways that we could do this. Either we could work really hard and design the AI in such a way that it never violates these requirements, which could be tricky. We could just train a regular AI, and then it might be interesting to try and prove that it doesn't violate these requirements and see the interesting cases where it does. And then also we could just put on a hard limit and say anything that the AI says that it wants to do that's outside of what you know is safe, you just disallow it. But this is a really big open question, and it might be useful to be able to use refinement in this space. So everything I've talked about so far is talking about static analysis that we do before we even build the system and before we deploy it. However, all of these static analysis process methods have the problem that Kathleen mentioned, which is that if in the real world doesn't match the model, the assumptions that we made, our differential equations, then none of the conclusions that we made still hold. So we have this last thing, and this is work that comes from Stefan Mitch and Andre Platzer here at CMU, called Runtime Monitoring. And they've made this tool, Modelplex, which basically says, okay, well, we've already done all of this analysis where we have this abstract model and we proved that it's safe. How do we know that our proof translates to this real world system? We can actually do that refinement check in real time. We can distill it down to small computationally tractable questions on the physical current state of the aircraft and check as the system is running that it actually refines the model we expect it to refine. This might not necessarily keep us safe. If we've violated the model, in some ways it's too late, but at least it gives us a really early warning system that, hey, you may not have a proof of the behavior that you're doing right now. And it could let us fall back to a fail-safe method. One final thought, which is that we have these controllers that are becoming increasingly intelligent. And as a result, we kind of want our theorem provers and our formal verification techniques to be able to improve at the same rate that our intelligent controllers are improving. So one question that's an open question is, can we use deep learning for theorem provers? And there are some preliminary results from Google that are called deep math, and we're working to where they've had some positive results for using neural nets to choose a selection for proving theorems. So thank you very much.